My name is Jiazhi Huang, and this is my demonstration for the CITS 322 Computer Networks project build. This project aims to build a feature-rich and secure network multiplayer battleship game. My implementation meets all 4 project tiers, from concurrency to advanced networking. Now let's walk through the demo tier by tier. First, let me demonstrate some simple features of tier 1. Now I start the server, which prompts for shared secure key for secure communication. So I enter the simple key. And there, the server has started successfully. Next, I launch 2 clients. Each client also requires the same shared key to establish a connection. Now, as you can see from the server logs, both clients have successfully connected. It looks like the timed out just happened. That's actually a feature I will show in a moment, but for now, let's continue with tier 1. Once a game begins, players first position their fleet, and I support both random placement for quick start and menu. All placement actions are validated by the server for legality. With the ships deployed, the players engage in turn-based combat. The players can fire at coordinates, for example B2, and the server decides the shot, broadcasting the result, whether it's a hit, a miss, or if empty. And both players' views of the game boards. Both players' views of the game boards are updated in real time. Now the game is over. So the game concludes when some player's fleet is completely destroyed, at which point the server declares the victor. So tier 1 set up a solid base, and tier 2 improves the gameplay experience and makes the server more scalable. The tier 2 makes the system much stronger. For example, it handles bad client inputs well. If I try to fire at a wrong coordinate or fire when it's not my turn, and the server sends back a clear error message. And importantly, the server stays stable. And to keep the games moving, I have added a player inactive timeout. So, if a player doesn't make a move in the set time, for example 60 seconds by default, the system automatically sets the timed out and the other player wins. And that's how the timed out works. This stops games from getting stuck. And as you can see, the bear game server can run many games once after another without restarting. After a match, players can stay connected and will be matched for new games from waiting queue. The system also handles basic disconnections. If a player suddenly disconnects during the game, their opponent gets a message. The better reconnection features are shown in tier 3. Now the player 3 is connected to the game, and what if a new client connect while a game is on? As you see, the new client is put in a waiting queue and can now watch the current game as a spectator. This works like a waiting lobby. Next, in tier 3, I will show how I handle more complex network situations, like a full spectator model and the very important player reconnection feature. So the beer server can handle multi-clients at the same time. Right now, 3 players are playing and the 4th client has joined automatically as a spectator. The spectators can see everything happening on a board in a real game, including the results from each turn. But to keep things fair, they can't control anything. If I try to fire from the spectator client, the server will just ignore it or show an error. And disconnects can happen often in an online game, so I added a reconnection feature. Now I reconnected the player, and as you can see, they are back in the game and everything just looked like before. So after a game ends, the system smoothly picks new players from the waiting queue, which might include the spectators or players from the last match, and starts the next game right away. Those were the main features I built for Tier 3. Next up, the next one is Tier 4, where I will show some advanced networking features like my custom protocol other security measures. To achieve finer control over communication and enable advanced features, I designed and implemented a custom binary network protocol, moving beyond simple TCP send. This protocol is my packaged class, features a 24-byte fixed header and a variable length payload. So using the Wireshark, we can visualize my custom protocol in action on the network. Here a TCP packet is carrying 266 bytes of my application layer beer protocol data. In the byte view, we can clearly identify the components of my header, starting with the 42 and 45 magic number for BE, followed by the version type, sequencing number, and so on. After the header fields comes the 4-byte CRC32 checksum, and the large block of data following the checksum is my encrypted application payload. Next, I will demonstrate the checksum error detection. So, I modified the client to visually introduce errors with a 20% chance per packet. It flips a bit in the first byte of the encrypted payload to simulate data corruption. So, as the client reports decrypted and send certain packets, and on the server side, the logs precisely show certain packets being rejected due to the checksum mismatch after corruption. This shows that my checksum works with 100% effectiveness in catching these big errors and keeping the data correct. The game also features an integrated instant messaging system. The players and the spectators can communicate in real time using the chat command. Messages are broadcast to all participants within the current game or other users in the waiting lobby. So, to ensure the confidentiality of communications, I have implemented an encryption layer for all packet payloads. I use a custom XOR-based stream cipher. To prevent replay attacks, the server uses sequence numbers as discussed in my T4.1 protocol overview. So that concludes the demonstration of my beer project. Kernel stands as an effective demonstration of applied networking principles and offers a solid foundation for future expansions. Thanks for your work.